Hello and welcome to this video where we are going to do variation of parameters in differential equation chapter. Okay, so let's quickly look at the theory of variation of parameters. It is saying that if we consider a second order differential equation which is given by something like this, okay, and you have to observe that this is a linear non-homogeneous second order differential equation. Okay, linear because all the constants, all of these coefficients are constants, and it is non-homogeneous because the right hand side is not 0, it is some function of x, and this is a second order differential equation. Okay, so usually we solve these kind of equations by d operator method, right? But if it is mentioned that you have to solve by variation of parameter, then this is the process that goes in. Okay, first of all we have to find out the complementary function. Okay, that's usually the same way we do in the d operator method. So first of all we are going to find the complementary function just like the usual. Then in the complementary function we are going to get two functions which are going to look something like this, y1 and y2, which is associated with the two constants. If those two y1 and y2 have to be linearly independent, now why that is necessary, I'm coming to that a bit later. Then the particular integral that we find out in d operator, without using all the properties of d operator, we can directly say that the particular integral is going to be u times y1 plus v times y2. Okay, the same y1 and the same y2. Now what is u and v? This is something that we have to find out using variation of parameter. U is given by minus of the integral y2 times q, where q is the right hand side of the differential equation, and this is the y2. So y2 times q by w, where w is given by this determinant over there, and similarly v is given by positive integration of y1 times q by w dx. Okay, so we have to find out u and v using these two formulas. Once we get the u and v values, we are going to plug it here in the particular integral. Okay, and w is the determinant y1 y2 and y1 dash y2 dash, where the dash represent the derivatives of y1 and y2. Now what was the requirement for y1 and y2 to be linearly independent? If it was not linearly independent, then this determinant would have become 0. Okay, so if y1 and y2 are independent, this determinant is definitely going to be non-zero. This determinant is called the Wronskian. Okay, it's the Wronskian of w1 and w2. Okay, so the Wronskian is non-zero if y1 and y2 are independent, and w or the Wronskian needs to be non-zero, otherwise the denominator is going to become 0 and we are going to get a problem over there. So if we are having two dependent y1 and y2 values here, then this process is not going to work out. Okay, we need to have y1 and y2 linearly independent. So this is the entire process. Okay, now we are going to apply this in a few problems. So let's look at our first problem. It is said that solve this differential equation. Obviously we'll solve it by variation of parameters. Now one more thing you can observe, if the same question was given in d operator method, okay, the video, if you don't know what's d operator method, then you will find a hyperlink over here for d operator and you can just check that out. So in d operator, if this was asked to solve, the problem would have been this right hand side, right? We don't have any shortcut or direct formulas to find out the particular integral in d operator method for trigonometry looking like this. We have formula for direct sin x, for direct cos x. If it is some other function, then the process was very lengthy using the conventional integrations, right? But there was no direct process for doing these kind of things. So here variation of parameter is going to be very easy. Okay, so the first thing what we have to do is find out the complementary function. Okay, so to find out complementary function, the first thing that we take is trial solution. So let me say that let y equals to e to the power mx be the trial solution of, so we don't take the trial solution of the original equation, we take the homogeneous part of the original equation. That means we make the right hand side 0 and take y equals to e to the power mx to be the trial solution of that equation, right? So be the trial solution of d2y dx square plus y, which is exactly same as the LHS, and the right hand side we're going to take that as 0, right? So the moment we take this as a trial solution, we are going to get an auxiliary equation. So therefore I'll directly write the auxiliary equation. I hope you people already know all these stuff, so I'm not going into the elaborate process of that. So how do we find out the auxiliary equation? Just a quick recap. We replace the order of the derivative with m raised to the same power. Like if we have a second order derivative, then the power of m is going to be 2. If we had a first order derivative, then the power of m would be 1. Okay, and where you have only y, we write that as simply 1, right? A whole e to the power mx common equals 0. It's now you might ask, how did we get this? The basic thing is just if you have y equals to the power mx, find out the double derivative, then add y with it, take it equal to 0, you will come down to this equation. That's simple, and this is the faster way of writing. The second order derivative replaced by m square, first order derivative replaced by m, y replaced by 1, okay, and a whole e to the power mx common. So obviously e to the power mx is always non-zero, so we will be having m square plus 1 equals 0. Since e to the power mx is non-zero, so that would give us m equals to plus minus iota, right? Achha, now if this was the complementary roots of the auxiliary equation, right, then our complementary function would have been c1 cos x plus c2 sin x, right? I hope you people remember this. If m was alpha plus minus I beta, then our yc would have been e to the power alpha x c1 cos beta x plus c2 sin beta x, right? This was the generalized thing. Here my alpha part is 0, so I don't have the e to the power alpha x part, and my beta value is 1, as you can see, so I have c1 cos x plus c2 sin x, right? So now I can compare this with my formula and say this is the y1 part and this is the y2 part, okay? Just in the formula I had mentioned that yc will be c1 times y1 plus c2 times y2, so my y1 and y2 values are nothing but cos x and sin x, okay? You can take the reverse one also, no problem with that. So let me mention that let y1 is cos x and y2 is sin x, okay? So now we are going to assume yp, that is the particular integral as per the variation of parameter formula. So I'm going to assume that let yp is u times y1 plus v times y2, and now we are going to calculate u and v, right? So I'm going to start the calculation with u, where u was minus of integration y2 times q by w. I hope you people remember this formula. I had written it just now. And here my y2 is sin x. And what is my q? My q is the right hand side part of the equation. That means the non-homogeneous part, and the right hand side part is this, right? So this is my q part, which is sec cube x into tan x, okay? So I'll just substitute that sec cube x into tan x. Achha, I also need the Wronskian at the same time, so without the Wronskian I cannot get the denominator. So I'll just quickly find out the Wronskian out here. So w was y1, y2, y1 dash, y2 dash, right? y1, y2 is cos x sin x, so that's cos x sin x. Derivative of y1 is y1 dash, so the derivative of cos x is minus sin x, and derivative of y2 is derivative of sin x is cos x. So if I take the determinant, you can just observe it's cos square x minus minus will become plus cos square x plus sin square x, right? So the value of the Wronskian in this case is 1, okay? So W value we have got 1 for this particular case. So I'll write just 1 over here. Achha, I just missed the dx out here. So integration of this dx, right? So that's going to be our u. So now let's just focus on this particular integration. I'll take 1 sec x from the sec cube. I have 3 sec x over here, 3 sec x multiplied. So I'll just take 1 sec x, and 1 of the sec x multiplied with the sin x, that will become a tan x, right? So say sin x into 1 sec x, that's becoming tan x. So I'm having tan square because I already had a tan x from before, and remaining are 2 sec x. So basically sec square x dx, right? Now in this integration we can make some simple substitution. We can make the substitution that z equals tan x. So that would give us dz equals to sec square x dx, right? So that can be a very simple substitution over here. So we'll be getting minus, in place of tan x I've taken z, so that's going to be a z square, and sec square x dx, that's going to be simply dz. So I will be having minus z cube by 3. Don't write any integrating constant over here because we are just finding out the particular integral that cannot have any constant. Remember that. Okay. So I'll just put back the value of z. So that's going to be minus 10 cube x by 3. So that's the value of u we have got. Okay. So the value of u is minus 10 cube x by 3. Now next we need to find out the v value. So the moment we have u and v, our problem is done. Okay. So now coming to the v part, the formula for v was y1 times q by w. Now what was my y1 part? You can just check it over here. I've written that my y1 part is the cos x part and the y2 was the sin x part. Okay. So cos x into q is same as the right hand side, which is sec cube x tan x whole divided by the Wronskian value is 1, and I've again missed the dx, so a dx out here. Okay. So now 1 of the cos x will get cancelled with 1 of the sin x. So what will be remaining is sec square x tan x dx, right? And I can use this same substitution down here, right? The same substitution that z equals tan x. If I substitute that, so I'll be having integration z and sec square x dx, that's going to be dz. So z square by 2, and that would be tan square x by 2. So that's our value of v. Okay. So we have got the value of u, we have got the value of v. Now we just need to put it in place of the yp and get the value of yp. Okay. So finally I can say that therefore my yp would be, it was u times y1 plus v times y2, and u value we have got is minus 10 cube x by 3. So u value is minus 10 cube x by 3, and y1 value is cos x. So that's our first part, plus v value is tan square x by 2, and the y2 part is the sin x. Okay. So basically this is our particular integral. So finally we can say that our general solution, the general solution y is given by yc plus yp. So y would be, yc was c1 times cos x plus c2 times sin x, plus yp is just this value. So that's going to be a minus tan cube x cos x by 3 plus tan square x sin x by 2, and that's our final answer. Okay. So that's how we have done the first problem using variation of parameter. Now we are going to the next problem and solve by the same method. Okay, so in the second question we have a second order differential equation. Here my right hand side q part is 9 e to the power x and the remaining is almost same as the previous one. So first again let's concentrate on finding the complementary function. So for complementary function we need to take a trial solution. So let y equals e to the power mx be the trial solution of, now how do we take the trial solution? We take the trial solution for the homogeneous part just like we have done in the previous question. So d2y dx square minus 3dy dx plus 2y equals 0, right? So we get the auxiliary equation and I'll write that directly. I told you before how to write it. The second order term is going to get replaced by m square, right? This term is going to get replaced by m square. The first order derivative, that's going to get replaced by simply the m term, and y is going to be replaced by 1, so I'll just have 2. Okay, so 2 times 1 I can say, so 1 is, we have got it from the y part, and entirely e to the power mx is going to remain common equals 0. So that's a faster way of writing it. And obviously e to the power mx is not going to be 0, so we're going to have m square minus 3m plus 2 equals 0, since the e to the power mx part is going to be non-zero. And if we just factorize this, I think it's going to be m minus 1 times m minus 2, and the roots are going to be 1 and 2, right? Now we're going to take the complementary function. So therefore complementary function is given by c1 e to the power x plus c2 e to the power 2x. I hope you remember the rule for this. If the m values were two distinct values, alpha and beta, two distinct roots, then yc would have been c1 e to the power alpha x plus c2 e to the power beta x, and this was the rule. So just by that rule we have got our complementary function. Okay, so now I can say this is my y1 part just like before, and this is my y2 part. Okay, so we're going to take that help, and now we're going to write that therefore, or I would say that let yp equals u times y1 plus v times y2, right, where y1 is the e to the power x part and y2 is the e to the power 2x part, right? We need to find the Wronskian before we can proceed with the integral. So the w is going to be y1, y2, y1 dash and y2 dash determinant. y1 is e to the power x, y2 is e to the power 2x. Derivative of e to the power x is e to the power x. Derivative of e to the power 2x is 2 e to the power 2x, right? So that would be, if we multiply, that would be 2 times e to the power 3x minus e to the power 3x, and that's ultimately going to be e to the power 3x. So our Wronskian value turns out to be simply e to the power 3x. So now let's go into the integrations to find out u and v. U is given by the formula which I had stated right before, minus of y2 times q by w dx. Okay, so minus of y2 is my e to the power 2x part is my y2, so e to the power 2x into q. My q value is going to be the right hand side of the equation. Let's just take a look. My right hand side of the equation was 9 times e to the power x, that was my q part. Okay, so 9 e to the power x I'll write in place of q. So 9 e to the power x by Wronskian value is e to the power 3x dx. You can see all the exponential part is going to get cancelled. What remains is 9 dx, so that's going to be simply 9x. Okay, very simple. Now the v part is going to be y1 times q by w dx, my y1 part is e to the power x, so e to the power x times q is 9 to the power x by the Wronskian, which is e to the power 3x dx. Here you can see all the e to the power x's are not getting cancelled. 1 e to the power x is going to remain in the denominator, so that's going to be 9 times e to the power minus x dx, because it's in the denominator, so the integration of that would be minus of 9 e to the power minus x. Okay, so we have got our u part, we have got our v part. Now we just need to put it in the yp part. Okay, in the yp equation we need to put it. So my yp is going to be u times y1 plus v times y2. So my u value is 9x and my y1 value is e to the power x plus v2. My v value is minus of 9 e to the power minus x times y2. My y2 value is e to the power 2x. So that's going to be a 9 if I can take entirely common, then 9, or I can take a 9 e to the power x entirely common, so I'll be having x and out here a minus 1, right? So this is my entire yp part. Okay, and finally we'll write the general solution. So therefore the general solution is given by yc plus yp. yc was c1 e to the power x plus c2 e to the power 2x plus yp is 9 e to the power x whole into x minus 1, and that's the entire solution using variation of parameters. Okay, I hope this video has been helpful. Thank you. Keep watching.